Hello physicists, in this video we're going to be talking about all the vector operations we covered geometrically on previous videos, how they apply to our unit vector notation that we derived last video. So when you multiply a vector when written in this unit vector notation in terms of I, j, and k, if I had a scalar value r, okay, r is a real number, a real scalar value, and I multiplied times a vector a. That means I'm basically multiplying by the vector written in unit vector notation, right? The vector sum inside the parentheses is the exact same thing as vector a itself. And when you multiply by the scalar value r, you could distribute r and you get r times axi plus r times ayj plus r times azk. So whenever you multiply a vector in unit vector notation by a scalar value, then each of the components increases by a scale factor r. Okay, so if we had, if we had vector a equal to 3i minus 4j plus 5k, okay, what is 3a? Well, 3a is just 3 times 3i minus 4j plus 5k. Three I minus 4j plus 5k. So we're multiplying all of this by 3. And by distributing, using normal algebra, we get 9i minus 12j plus 15k. So you're adding 9 times the unit vector I. Okay, you're adding it to negative 12j, so 12 times j pointing in a downward direction plus 15k. And so 15 times the k unit vector. And that is the resulting vector 3a. Now, vector addition is also incredibly simple. Suppose you had vectors a and b and wanted to add vectors a and b. That means you're just adding vectors axi plus ayj plus azk. And if we consider the component to be bxi plus byj plus bzk, this is basically what you're doing. Then it's just like normal algebra, just like adding like terms. You get ax plus bxi plus ay plus byj plus az plus bzk. Okay, and vector subtraction is also basically the same thing. If you're subtracting vectors a and b, then it is just subtracting like terms. Okay, so if I write out all the vectors in unit vector notation, then I get ax minus bxi plus ay minus byj plus az minus bzk. So you're just adding and subtracting like terms when you're in unit vector notation. So let's do another example. Let's have vector A equal the same vector we did above, 3i minus 4j plus 5k. And vector B is equal to I minus 2j plus 4k. What we want to do is find both A plus B and A minus B. Now, A plus B is equal to 3i minus 4j plus 5k plus I minus 2j plus 4k. And that results in 4i, 3i plus I is 4i, minus 6j, negative 4 plus negative 2 is negative 6, plus 9k. 5k plus 4k is 9k, adding like terms. Similarly, if we were to subtract the two vectors, write them out in unit vector notation, and you just subtract the like terms as you would with actual variables. So 3i minus I is 2i, negative 4j minus negative 2j is negative 2j, and 5k minus 4k is just k. So we get A plus B is 4i minus 6j plus 9k, and A minus B is 2i minus 2j plus k. Now, the dot product in unit vector notation is a bit different in that it's not as obvious what it is, but it is not that hard once. It's not that hard to remember what it is. So if I were to take the dot product, this is the final operation we discussed prior to learning about unit vector notation. If I were to take the dot product of A and B, that's AXI plus AYJ plus AZK dot BXI plus BYJ plus BZK. Now, you could remember I said the dot product had a distributive property, right? So you could easily derive this expression by distributing and multiplying as you would with actual polynomial terms, as you would in math. And you realize that anything I dot j, I dot k, and all of that, because I, j, and k are perpendicular to each other, they'll result in the dot product being 0. So what you get as a result of multiplying out and simplifying is A dot B is equal to AX times BX plus AY times BY plus AZ times BZ. Okay, and this is the dot product when written in the unit vector notation. This is the dot product. So similarly, you can just multiply everything out, and you get this expression. So if A is 3i minus 4j plus 5k, so we're going to use the same example vectors above, and B is I minus 2j plus 4k, then A dot B, we just used a formula. And it's easy to remember because it's the product of the x components plus the product of the y components of each vector plus the product of the z components of each vector. So there's no mixing up. Okay, so it's very simple to remember. So the x component of A times the x component of B plus the y component of A times the y component of B plus the z component of A times the z component of B. Okay, and what do we get as a result? We have 3 times 1 is 3, plus 8, negative 4 times negative 2 is positive 8, plus 20. So we get 3 plus 8 is 11, plus 20 is 31. So the dot product A dot B of these two vectors, they are equal to 31. Okay, so those are all the operations. Those are all the main operations we discussed, all in the unit vector notation. Okay, so we have a dot product, vector addition, and vector subtraction. Sorry for that, and vector multiplication by a scalar. Thanks for watching. See you next time.